An air bubble formed under water at temperature 17 degrees Celsius and the pressure 1.8 atmosphere started to move upwards and reach the surface where the temperature is changed, it is 27 degrees Celsius and pressure becomes 1 atmosphere. The volume of the bubble at the surface will become. It's a simple application of ideal gas equation, that is PV is equals to nRT, and in this case we can easily relate volume with temperature and pressure, because in this case the same gas bubble was there. It means number of moles are same, R value is also same. So this V is basically dependent on temperature, directly dependent on temperature, and inversely dependent on pressure. Suppose I'm talking about the first condition, when the bubble was underwater and when the temperature was 17 degrees Celsius and the pressure was 1.8 atmosphere, more pressure was there. So this V1 in that condition is directly proportional to the temperature, that is 17 plus 273, it would be 290 divided by pressure, that is 1.8 atmosphere. Simply, in the next condition, when the bubble is at the surface of water, that V2 is directly proportional to 300, that's the temperature, divided by the pressure, that is 1 atmospheric pressure or 1 atm. Now let's divide V2 by V1, that would be equal to 300 divided by 290 into 1.8. So the value of V2 is equals to 1.86 into V1. And with the help of this, you can easily identify that the volume of bubble at the surface will become 1.86 times of initial volume that we have considered here as V1. And that's why answer is option 2. And yes, it's a turn for question number 67. Compressibility factor under critical state of a gas is. So we are just going to talk about the compressibility factor at critical state. So I'm just considering it as ZC, that is equal to PC VC upon RTC. It means we are considering pressure as the critical pressure, critical volume and the critical temperature. And here we should know that when we talk about VC, that is critical volume, that is equal to 3B. What about critical pressure? That is equal to A upon 27 B square. And then third thing is TC, that is equal to 8A upon 27 RB. So all these values we have, let's find out. The value of ZC is equals to PC value, that is A upon 27 B square into BC is 3B, then R, that's here, and further we have TC value also. That TC value is 8A upon 27 RB. Let's check. In this case, A would be cancelled from here and further B is cancelled. Then 27 is also cancelled and we are left with 3 by 8. And this 3 by 8 is the answer for this question. That's why I'm marking it as the correct answer. That's option 4. Let's take question number 68. Ratio of the rate of effusion of oxygen gas at 1.5 atmosphere to that of helium at 4.5 atmosphere will be. So this is the question in which we are talking about the rate of effusion, and that rate of effusion is directly proportional to the pressure on the gas and inversely proportional to the molar mass of the gas. So in this case, we have to just find out the ratio of the rate of effusion of oxygen gas to that of helium gas, and that would be equal to the pressure of oxygen gas upon molar mass of oxygen gas divided by pressure of helium gas. Further, it's divided by the molar mass of helium gas. This is the formula that we are just going to apply here. So in this case, this pressure of O2 is given in the question, 1.5. Molar mass of helium we already know, that is 4 gram per mole. Molar mass of oxygen is 32. Further, pressure of helium is also given in the question, that's 4.5. So it would be equal to 1/3 into 2 upon 4 root 2, and that would be equal to 1 upon 6 root 2. So this is the ratio of rate of effusion of oxygen to the rate of effusion of the next gas. What is that? That is helium. So the ratio that's given here is 1:6 root 2. Where it's given? It's given in option 1, and that's why the answer is also option 1. Now let's check question number 69. Question number 69, standard enthalpy of formation is 0 for. We have different options given here, and we should always know that naturally occurring most stable form of an element has 0 standard enthalpy of formation. And if you look at the given options, if you talk about diamond, it does not have standard enthalpy of formation as 0 because it is not considered as naturally occurring most stable form of carbon. Further, for O3, the same is the case, and Br negative is the same case also. Which is the correct option? If we talk about chlorine, this is the standard state of chlorine, and that's why this is the correct answer for this question. Let's take next question. The work done by 1 mole of ideal gas when its temperature is increased by 1 degree Celsius at constant pressure is. We should know that we are talking about ideal gas. It's 1 mole we have, and its temperature is increased by 1 degree Celsius at constant pressure. The conditions are also given, and we know that dW is equal to minus dPV. This formula we are just going to use here. It can also be written as minus d nRT, and if we talk about W, it would be minus nR delta T. The formula that we are just going to use here. So this would be minus n. It means n is the number of mole, 1 mole is there, R is there, and what about delta T? This is the change in temperature, that is 1 degree Celsius. Now it would be minus R, and if we talk about W, it would be minus R here. So the work done by ideal gas is R. Where it is given? It is given in option 3, and answer for this particular question is also option 3. Let's check the next question.